Pluto, once perceived as an unmistakable and substantial planet in our planetary group, was for a long time thought of as a unique element. However, as of late, conversations led by famous astrophysicists Neil deGrasse Tyson and Michio Kaku have put Pluto back under examination, igniting renewed interest in its status. These specialists have proposed that Pluto might be on a potential impact course with Neptune, a hypothesis that has stirred up many inquiries. How might such a massive impact occur? What might the consequences be for both planets and for the planetary group? Are we witnessing a peculiar vast phenomenon, or is there a more complex and significant explanation behind this thought? Let's explore what such a potential Pluto-Neptune impact could mean for us. Once considered a smaller, more distant object in the planetary group, Pluto continues to generate much interest among researchers. According to extensive examinations from leading experts, Pluto's orbit is perilously close to Neptune's. This has led some astrophysicists, including Tyson and Kaku, to raise alarms about the possibility of a catastrophic collision between the two bodies. The pressing question now is, could such an event present a genuine risk to Earth? How could it even happen? Pluto's orbit is one of the most unique in our solar system. It takes a remarkable 248 years to complete a single orbit around the Sun, which means that since its discovery in 1930, Pluto has yet to complete one full cycle. However, that is not the only unusual feature of Pluto's orbit. It is elongated in shape, unlike the more circular orbits of the larger planets. Furthermore, Pluto's orbit is tilted at a 17 degrees angle compared to the plane of the solar system, making it one of the most tilted orbits observed in space. This extreme tilt, combined with its irregular shape, adds complexity to its journey through space. One particularly fascinating aspect of Pluto's orbit is its interaction with Neptune's orbit. For around 20 years during each orbit, Pluto actually comes closer to the Sun than Neptune does, defying expectations about the relative positions of these planets. This raises a critical question. Why haven't Pluto and Neptune collided? The answer lies in the gravitational forces at work within the solar system. Pluto's orbit was a mystery to astronomers following its discovery. Unlike other planets whose paths remain nearly flat and aligned along the solar system's plane, Pluto's orbit is tilted and elliptical, making it a subject of intense study. The fact that Pluto's orbit crosses Neptune's does not automatically mean a collision will occur due to a gravitational interplay that stabilizes the two orbits. This equilibrium, known as the three-body problem, refers to the way three celestial bodies, Pluto, Neptune, and the Sun, interact through their gravitational pulls. Predicting the future paths of these bodies is challenging, as it involves accounting for their current positions and the gravitational forces they exert on one another. In Pluto's case, this phenomenon reveals how its orbit, Neptune's orbit, and the Sun's gravity all work in a balanced manner to prevent a collision. Astrophysicists have pointed out that the stability of the Pluto-Neptune orbital interaction is aided by a mechanism called libration. In this context, when Pluto crosses Neptune's orbit, it does so at a distance of at least 90 degrees away from Neptune, meaning that the two bodies will never be in the same place at the same time. There is also the phenomenon of degree libration, which refers to the swaying or shifting of Pluto's orbit around its path. This means that Pluto does not cross directly into Neptune's orbital plane, further minimizing the risk of a collision. Another significant factor contributing to Pluto's orbital stability is the gravitational wobble phenomenon known as VZK wobbling, named after the scientists who analyzed how celestial bodies move in space. This effect explains how Pluto, Neptune, and the Sun influence each other's movements through gravity, helping keep Pluto's orbit stable. Despite Pluto's seemingly unpredictable movement, the combined forces at work ensure that its path remains relatively consistent over long periods. The three-body problem and the forces governing these celestial movements are crucial for understanding how planetary orbits evolve over time. These interactions between Pluto, Neptune, and other bodies not only help us learn more about Pluto, but also offer insights into the broader workings of our solar system. Mathematical simulations conducted in the late 1980s revealed that although these stabilizing forces help maintain Pluto's orbit, slight variations in its initial conditions could cause its orbit to become more erratic over extended periods. However, despite these potential irregularities, Pluto's orbit remains relatively stable over the years. Recent computational models have further illuminated the ways in which Jupiter, Saturn, and Neptune stabilize Pluto's path. For example, Neptune and Pluto are in a resonant orbit, meaning that for every 2 times Pluto orbits the Sun, Neptune completes 3 orbits. This resonance is crucial for maintaining the stability of Pluto's orbit. However, Neptune is not the only planet that influences Pluto's path. Jupiter's gravitational pull also plays a significant role. Even Saturn has been shown to contribute to the stability of Pluto's orbit. These simulations suggest that the gravity of Jupiter alone is strong enough to maintain Pluto's trajectory for billions of years, if not indefinitely. The interaction between Neptune, Jupiter, and Saturn is therefore critical in ensuring that Pluto remains on its stable orbital course. Without these stabilizing forces, our solar system will be far more chaotic, with objects like Pluto potentially colliding with other bodies or being ejected from their orbits entirely. The study of such interactions not only helps us understand Pluto's orbital mechanics, but also provides valuable insights into the broader functioning of the universe. Considering this understanding, Pluto's orbit becomes even more significant when evaluating hypotheses about a possible impact with Neptune. The study of Pluto's complex orbit demonstrates the dynamic nature of the solar system and how the forces acting on one celestial body can influence the entire system. It also serves as a reminder that even orbits that appear chaotic can still achieve a state of equilibrium through these intricate interactions. The concept of orbital resonance is key to understanding the delicate balance that exists within Pluto's orbit. This principle explains how Pluto's position and velocity, even in an irregular path, can still maintain a stable orbit over time. Programs that simulate these orbital mechanics have provided potential insights into how Pluto's orbit interacts with those of other celestial bodies, including Neptune. Small changes in the parameters of these models can show how tiny variations in Pluto's position or velocity can significantly alter its orbit over time. Despite the stabilizing forces that maintain Pluto's orbit, such as asymmetric libration and degree libration, its path can still be highly unpredictable. Even slight changes in Pluto's initial conditions or velocity can lead to significant shifts in its long-term trajectory. However, despite this apparent unpredictability, Pluto's orbit remains remarkably stable over billions of years, indicating that there is an underlying order to its movement around the Sun, even if it appears chaotic. Tyson emphasizes that while gravitational forces create a delicate balance within the solar system, the long-term evolution of planetary orbits remains uncertain. Although current models suggest that Pluto and Neptune are unlikely to collide, even minor gravitational disturbances from passing celestial bodies or distant stars could alter their trajectories. This potential for orbital shifts, though improbable on human timescales, underscores the dynamic and ever-changing nature of space. Michio Kaku, another renowned astrophysicist, expands on this perspective, highlighting the importance of advanced simulations and long-term observations. Kaku points out that gravitational resonances, while stabilizing, are not immune to disruptions caused by external factors. For instance, interactions with distant Kuiper belt objects or hypothetical Planet 9 could introduce subtle perturbations that accumulate over millions of years, gradually shifting Pluto's orbit. Furthermore, the gravitational influence of the Milky Way galaxy itself plays a role. As our solar system orbits the galactic center, it periodically passes through regions of varying gravitational density. These galactic tides can nudge objects like Pluto, altering their orbits in ways that are difficult to predict. Although such influences are weak compared to the gravitational forces within the solar system, their cumulative effects over billions of years could potentially disrupt orbital resonances. Recent advancements in computational astrophysics have allowed scientists to simulate these complex interactions with greater accuracy than ever before. Using high-powered supercomputers, researchers can model the gravitational interplay between thousands of celestial bodies, projecting their movements millions of years into the future. These simulations suggest that while Pluto's current orbit is stable, even a slight deviation in its velocity or position could lead to unpredictable outcomes over geological timescales. One notable simulation conducted by the European Space Agency, ESA, explored various scenarios involving gravitational perturbations from passing stars. The results indicated that, under rare but possible conditions, a close encounter with a rogue star could alter Neptune's orbit just enough to bring it into closer proximity with Pluto. Although the probability of such an event is exceedingly low, it highlights the inherent uncertainty in predicting the long-term stability of planetary orbits. Despite these potential risks, both Tyson and Kaku emphasize that any significant changes to Pluto's orbit would unfold over millions, or even billions, of years, posing no immediate threat to Earth. Nonetheless, studying these interactions provides valuable insights into the broader dynamics of our solar system, helping scientists refine their models and improve our understanding of orbital mechanics. Moreover, exploring Pluto's orbit has implications beyond planetary collisions. Understanding how gravitational forces shape the trajectories of celestial bodies is crucial for predicting the movement of comets and asteroids that pass near Earth. By applying the same principles used to study Pluto, astronomers can identify potential impact threats and develop strategies to mitigate them, enhancing planetary defense efforts. As technology continues to advance, future space missions may offer even greater insights into Pluto's orbit and its interactions with Neptune. Upcoming telescopes, such as the James Webb Space Telescope, JWST, and next-generation observatories like the Vera C. Rubin Observatory, will provide unprecedented views of the outer solar system. These instruments will allow scientists to monitor Pluto's position with unparalleled precision, further refining our understanding of its long-term trajectory. Additionally, future space probes could explore the Kuiper Belt in greater detail, shedding light on the region's gravitational dynamics and their impact on Pluto. Building on the success of NASA's New Horizons mission, which provided the first close-up images of Pluto in 2015, next-generation spacecraft could study the gravitational forces at play in this distant region of the solar system. By gathering more data on Pluto's interactions with nearby objects, scientists can better predict how its orbit may evolve over time. In conclusion, while the possibility of a Pluto-Neptune collision remains highly unlikely, studying the gravitational forces that govern their orbits offers valuable insights into the broader workings of our solar system. The delicate balance maintained by gravitational resonances illustrates the intricate interplay between celestial bodies, revealing the hidden order underlying their seemingly chaotic movements. As researchers continue to refine their models and gather new data, our understanding of Pluto's orbit and its place within the cosmic tapestry will continue to evolve, deepening our appreciation for the dynamic and interconnected nature of the universe. Tyson, who assumed a vital part in renaming Pluto from a planet to a bantam planet, underlines the significance of constantly developing our comprehension of divine mechanics. He trusts the renaming of Pluto was not a misfortune, but rather an important change as our knowledge of the solar system expands. Tyson sees Pluto's surprising orbit and its interactions with Neptune as a demonstration of the unpredictability of space. While he acknowledges that Pluto's orbit is stable for now, he cautions that it could change altogether in the future. This possibility highlights how much we still need to learn about the forces that shape the planetary system and the extensive ramifications of those forces. Tyson's point of view emphasizes the unpredictable and ever-changing nature of space, reminding us of the intricacies of heavenly mechanics. His examination of Pluto's orbit, particularly in relation to Neptune, highlights how even long-studied planetary movements can still hold surprises. Despite the apparent stability of Pluto's current orbit, He suggests that the situation could evolve over time due to the dynamic forces at work within the solar system. Tyson contends that our understanding of these forces and their influence on celestial bodies is far from complete, making the investigation of Pluto and similar objects significantly more captivating. The renaming of Pluto as a dwarf planet, a move that was met with controversy by some in the public, actually aligns with our growing comprehension of the solar system. Tyson explains that this change was an important step in refining our classification system for celestial bodies. As our tools for exploring the universe improve and our knowledge expands, it becomes clear that Pluto, while no longer officially considered a full-fledged planet, remains a significant subject for scientific examination. This evolving understanding isn't limited to Pluto's classification. It extends to broader questions about the stability of our solar system and the forces that govern the movements of planets, moons, and other objects. The work of scientists like Tyson and Kaku continues to shed light on the complexities of celestial mechanics and their implications for the future of our solar system. These discussions, though rooted in the specific case of Pluto, have broader relevance for understanding how the universe works. Kaku, another key figure in the discussion about Pluto and Neptune, offers additional insights into the potential risks and dynamics at play. His perspective builds upon the work of Tyson and others, exploring how even small changes in Pluto's orbit could potentially lead to a collision with Neptune or affect the stability of other celestial bodies. Kaku's work helps illuminate how we might be able to anticipate and possibly mitigate such risks, even as we continue to expand our understanding of the solar system's most distant objects. As scientists work to better comprehend the possibility of a future collision between Pluto and Neptune, they rely on advanced simulations and models to predict how the gravitational forces acting on these two bodies will evolve over time. These simulations help researchers track the movement of Pluto and Neptune, taking into account the complex interactions between their orbits and the influence of other planets like Jupiter and Saturn. Such research is crucial not only for understanding Pluto's future, but also for improving our ability to predict the behavior of other objects in the solar system. Despite the relatively stable relationship between Pluto and Neptune at present, there is still considerable uncertainty surrounding the future of their orbits. The intricate gravitational dance that keeps Pluto and Neptune on their current paths could, over long periods, shift. Even the slightest variation in the initial conditions of their orbits could cause their paths to diverge, leading to potential collisions or other disruptive events. This unpredictability highlights the limitations of our current knowledge and the challenges that lie ahead in studying the long-term dynamics of the solar system. Understanding the forces that influence Pluto's orbit is just one piece of the puzzle. It also provides valuable insights into the broader dynamics of our planetary system. The relationship between Pluto and Neptune serves as an example of the delicate balance required to maintain the stability of planetary orbits, not just for these two bodies, but for the entire solar system. In this sense, the study of Pluto's orbit is essential for gaining a deeper understanding of how celestial bodies interact with one another and how the solar system as a whole remains in balance. As we continue to explore space, the study of Pluto and other distant objects becomes increasingly important. These objects, though far from Earth, hold clues that could help us understand the origins and future of our solar system. By examining Pluto's unusual orbit and its potential interactions with Neptune, scientists are learning more about the forces that shape our cosmic neighborhood. These insights may have implications not only for our understanding of Pluto, but also for the study of other distant objects, including exoplanets and stars in faraway galaxies. The ongoing investigation into Pluto and Neptune also serves as a reminder of the need for continuous learning in the field of astronomy. Just as Tyson and Kaku have adjusted their views in light of new discoveries, future generations of scientists must remain flexible and open to new ideas. The universe is constantly changing, and our understanding of it must evolve as well. As technology advances and our exploration of space expands, we will likely uncover even more surprises about the nature of planetary orbits and the forces that govern them. In conclusion, the The potential for a collision between Pluto and Neptune is an intriguing and complex subject that continues to captivate scientists and the public alike. The unique orbital characteristics of Pluto, combined with the complex gravitational interactions at play, make this a topic of great interest. While the current stability of Pluto's orbit is reassuring, the possibility of future changes serves as a reminder of the unpredictable nature of space. As we continue to study Pluto, Neptune, and the other objects in our solar system, we gain deeper insights into the mechanics of our cosmic neighborhood. These insights not only enhance our understanding of the past and present, but also shape our predictions for the future, helping us better comprehend the vast and dynamic universe we inhabit.